Welcome to this third lecture in the series on tensor analysis. To begin with, we will focus here on vectors and covectors under Lorenz transformations. These are, of course, the building blocks for the mathematical theory of special relativity and as such are very important for us physicists. We will explore how the existence of an invariant inner product allows us to connect a vector with its corresponding covector and vice versa. In the language of components, this is called lowering or raising of indices. We are going to see the connection between the existence of a metric with this concept of lowering or raising of indices. We will then move on to talk about similar considerations for general linear transformations. In this process, we will meet the metric tensor, which will be our first non-trivial example of a tensor beyond rank 0 and rank 1. While a proper full theory of tensors of higher rank will have to wait till the next lecture, here we at least make a beginning and try to motivate why this kind of an object should be considered a tensor of rank 2. Or more precisely, a tensor of rank 0, 2. But before we go on to all these, let us look back at what we have learned from the previous lectures. Before we begin today's lecture, let me quickly recapitulate what we have covered so far. We have been talking about vectors and covectors under general linear transformations as well as general coordinate transformations. Under general linear transformation, where the column vector x goes over to the column vector x prime given by the matrix S acting on x, here x is a column vector which contains all the coordinates x1, x2, x3 up to xn in n-dimensional space, or x0, x1, x2, x3 for example in 1 plus 3-dimensional spacetime. This expression written in terms of components can be written with x with an upper index I going over to x prime I, and in keeping with the Einstein summation convention with the added demand that you only sum up indices which are repeated once as a suffix and again as a superfix. The ijth element of S is written this way: Sij with the indices I and j going from top left to bottom right. So x prime I is Sij xj, written this way. And under such a coordinate transformation, vectors are n-component objects which transform essentially in the matrix language as follows: A goes over to A prime given by S acting on A, or in terms of components, this is A upper I going over to A prime upper I, S I j A j, where once again the S indices are written in this particular manner from the top left to the bottom right. And written in this manner, Sij stands for the ijth element of the matrix S. And of course, the reason why we have chosen to use superfixes for indices here is that there happens to exist another kind of n-component object which you can write similarly like a column vector, for which the indices are written downstairs. These are the so-called covectors. Under general coordinate transformation, covector B written in the matrix form will go over to B prime, which is S transpose inverse acting on B. This particular choice of S transpose inverse is designed to ensure that B transpose A or A transpose B are scalars. And the components of B are written, as I have said, with a lower index B lower index I goes over to B prime lower index I, and that is written as Sij Bj, where the ij indices now go from bottom left to top right, the other diagonal, and The important point to note is this particular Sij, where the indices are written in this way, the diagonal slanted upwards, is actually the ijth element not of S but of the matrix S transpose inverse. Now, with this convention in place, it is easy to see that Sij, Sik, where the sum is over the first index, but with the two S's of two different kinds, one with indices from top left to bottom right, the other with indices from bottom left to top right, as well as Ski, Sji, again two different kinds of S matrix elements, with now the sum being done over the two column indices. They are both equal to delta Kj, the Kjth element of the identity matrix, and an immediate consequence of this relation is that Ai/Bi, the contraction of the vector Ai with the covector Bi, goes over under a coordinate transformation to A'I, B'I, which is the same as Ai/Bi, which is the statement that this quantity is a scalar. Now, this is for a general linear transformation. A very special kind of linear transformation would be rotations, or you could even include reflections in that, orthogonal transformations. And the basic idea there is that under an orthogonal transformation, S and S transpose inverse are exactly the same matrices. So you cannot distinguish between vectors and covectors, which is why when we dealt with vectors under rotation, which is the kind of vector that we dealt with almost all our lives, we did not need to worry about covectors, and we always wrote vector indices downstairs. There was no need for two different kind of vector indices to stand for two different kind of objects. Now, if we move over from general linear transformations to general coordinate transformations, where the coordinates x1, x2 up to xn goes over to new coordinates x'1, x'2 up to x'm, but this time the coordinate transformation equations are not necessarily linear, but they are smooth and at least locally invertible. The result that we get is, although the coordinate transformations may not be linear, the coordinate differentials transform linearly. Dx prime I is del x prime I del xj dxj, and an immediate consequence of this would be that vector components transform in this manner. A prime I is del x prime I del xj aj. So all you have to do is replace the dx's by a's and dx primes by a primes, and you have got the vector transformation equation. The covector transformation equation, on the other hand, goes b prime lower I is del xj del x prime I bj, and as we had shown in the last lecture, if del x prime del xj is the ijth element of the Jacobian matrix capital J, then del xj del x prime I is actually the ijth element of capital J transpose inverse. So in that sense, the general coordinate transformations essentially replicate the same results as for general linear transformations. If the vectors transform according to a particular matrix, the covectors transform, or the covector components transform according to that matrix's transpose inverse. And let me just remind you that this rather ugly S transpose inverse form occurs simply because we are writing both the vector and covector components as column vectors. If we had instead written covector components in the form of a row vector, the transform would simply have been B goes over to B prime, now a row vector, equals B times S inverse. And this brings home the fact that vectors and covectors transform oppositely to each other. And as a result of this, when a covector acts on a vector, the result that it yields is actually a scalar, something which does not transform at all, because the transformation of A and the transformation of B, the vector and the covector, cancel each other out. Now, while what we had said above about general linear transformations works equally well for all linear transformations, the particular kind of non-orthogonal transformation that we will deal with most is a very familiar one in physics, and it is none other than one of our most important symmetry transformations, the Lorentz transformation, the connection between one inertial observer and another. And let me quickly recap this that we had already discussed in previous lectures. The reason why a Lorentz transformation is not orthogonal is that under a Lorentz transformation, the quantity x0 square plus x1 square plus x2 square plus x3 square is not an invariant. What is an invariant, on the other hand, is the quantity x0 square minus x1 square minus x2 square minus x3 square. So, while Lorentz transformations are not orthogonal because the sum of squares of the coordinates is not invariant under Lorentz transformations, they are very nearly orthogonal. In fact, in the last lecture, we talked about a way in which you could make Lorentz transformations orthogonal, or rather, could make it look like it's an orthogonal transformation. The idea was simply to use I times x0 instead of x0 as the coordinate x4. This exactly is what Hermann Minkowski did when he first introduced Minkowski spacetime. And while it was a big hit at the time, making Lorentz transformations essentially look no different from rotations, it has slowly fallen out of use simply because the difficulties introduced by the imaginary time actually outweighed the advantages of making the transformation look like an orthogonal one. Now, under this particular transformation, x prime equals Lx, x prime mu, the muth coordinate, is written as lambda mu nu x nu, where once again the mu nu indices go from top left to bottom right, and the coefficient lambda mu nu stands for the mu nuth element of the matrix L. Also, the other important point, which I'm pretty sure most of you remember, is that the index mu, nu and other indices, other Greek indices, are actually meant to go from 0 to 3. Whereas in the context of special relativity, if we use a Latin index, then it usually goes over the spatial coordinates 1, 2 and 3. Now, under this particular transformation, vectors will transform according to the formula a prime upper mu is lambda mu nu a nu, just the same way as coordinates do. And of course, in the matrix form, you can write this as a prime equals L times a. On the other hand, covectors transform like the following. In the matrix form, B prime is L transpose inverse B. Once again, this particular form comes in because you're writing B as a column vector. If you had wrote it as a row vector, the transformation would have been B prime equals B L inverse. In terms of components, B prime mu is lambda mu nu B nu, where the indices mu and nu go from bottom left to top right, and this is the mu nuth element of L transpose inverse. So, if the indices go from top left to bottom right, then what is indicated is the mu nuth element of L. If the indices go from bottom left to top right, what is indicated is an element of L transpose inverse. Now, while this is exactly consistent with the convention that we had introduced before for general non-orthogonal transformations, what we will explain next will sort of reveal why this particular kind of convention is used. And it turns out that there is a way in which you can raise or lower indices. Now, this method of lowering or raising of indices is actually meant to yield components of a covector corresponding to a vector or vice versa. However, it so turns out that if you were to apply this method to, say, a lambda mu nu and lower this index while raising this one, it will give you lambda mu nu with indices going this way. And so, the whole process ends up being self-consistent. But before we can talk about that, we need to understand exactly what it means to have a covector corresponding to a given vector. And for that, we have to essentially examine the notion of how you can produce a number out of two vectors. In other words, we have to talk about a scalar product of two 4 vectors. From the fact that x0 square minus x1 square minus x2 square minus x3 square is a scalar under Lorenz transformations, it should seem reasonable that given two 4 vectors A and B, the quantity A transpose eta B, which is A0 B0 minus A1 B1 minus A2 B2 minus A3 B3 will turn out to be a scalar. And this is what we mean when we say the scalar product of two 4 vectors. Now let us verify the claim that this is indeed a scalar. So under a Lorenz transformation, the quantity A transpose eta B transforms to A prime transpose eta B prime, and of course A prime is LA and B prime is LB, so this becomes LA transpose eta LB, and using the standard property of transposes, this becomes A transpose L transpose eta LB, and from the standard property of Lorenz matrices that L transpose eta L is actually eta, it turns out that A prime transpose eta B prime is exactly the same as A transpose eta B. In other words, the quantity A transpose eta B does not change when you carry out a Lorenz transformation, and hence it is a scalar. It is instructive to actually be able to do this calculation using components. In terms of components, this quantity A0 B0 minus A1 B1 minus A2 B2 minus A3 B3 can be written in the form A mu eta mu nu B nu, where mu and nu are both upper indices or vector indices. Under a Lorenz transformation, this becomes A prime mu eta mu nu B prime nu, and using the fact that A prime mu is lambda mu rho A rho and B prime nu is lambda nu sigma B sigma, what we get is this expression. Now we can move the eta mu nu and lambda nu sigma to the front to get eta mu nu lambda mu rho eta nu sigma A rho B sigma. And using the basic property that we had talked about, that eta mu nu lambda mu rho lambda nu sigma, summed up of course over mu and nu as the summation convention demands, gives you eta rho sigma. And so the transformed quantity A prime mu eta mu nu B prime nu turns out to be exactly equal to eta rho sigma A rho B sigma, which is another way of saying that under a Lorenz transformation, the quantity A mu eta mu nu B nu does not change. So we have established once again, this time in the language of components, that this quantity is a scalar. To summarize then, for two 4 vectors A and B, the quantity A transpose eta B is a scalar, and in terms of components, this means that the quantity eta mu nu A upper mu B upper nu is a scalar. Now, if keeping the 4 vector A fixed, we replaced B by a linear combination. Let's say alpha 1 B1 plus alpha 2 B2, where alpha 1 and alpha 2 are scalars, and B1 and B2 are two 4 vectors, then the result, of course, will end up being alpha 1 times A transpose eta B1 plus alpha 2 times A transpose eta B2. In other words, replacing B by a linear combination gives us a resulting number which is a linear combination of the corresponding results. So A transpose eta acts on B linearly to produce a scalar. But that is exactly what a covector is supposed to do. So a row vector A transpose eta represents a 4 covector. And if we were to write this in the terms of a column vector, the transpose of A transpose eta transpose, which is a column vector, is simply eta transpose acting on A, and since eta is a diagonal and hence symmetric matrix, this is the same as eta acting on A. So if you take a 4 vector A and act upon it by the matrix eta, what you end up with are components of a 4 covector. Or if you were to write this in the language of components, eta mu nu A nu summed up over nu will give me 4 numbers which form the 4 components of a covector, and we denote this covector by exactly the same letter as the original vector. That is, since the original vector is called A, the covector will also be called A. It's after all the covector version of this object A, and we will write the components with a lower index mu. So we end up with A lower index mu equals eta mu nu A upper index mu. And once again, notice that we are using the upstairs downstairs convention when it comes to the summation convention, and the C index mu matches on both sides. Now note that what this has done is application of eta mu nu has lowered the index nu and changed it into mu. So this is what we mean by lowering of an index which changes the components of a 4 vector into the components of a 4 covector. Or in older language, changes the components of a contravariant vector to those of a covariant vector. Now, while we are not really going to use the terms contravariant and covariant, you are going to meet these terms often in various textbooks, so it is important that you are familiar with these terms, and which is precisely why I am going to lapse into that terminology from time to time. Now, since eta is simply plus 1, minus 1, minus 1, minus 1 down the diagonal, all that multiplication by eta does is that it keeps the A0 component unchanged and changes the sign of A1, A2 and A3. So A lower mu, or rather its 4 components, A lower 0, A lower 1, A lower 2, A lower 3 are nothing but A upper 0 minus A upper 1 minus A upper 2 minus A upper 3 in that order. So this process of lowering of indices keeps the temporal component or the 0 component the same and changes the sign of the spatial component. So converting a 4 vector to a corresponding 4 covector is pretty straightforward. All you have to do is just change the sign of the spatial components. Components number 1, 2 and 3. Of course, you can go the other way also. If B represents a covector, then eta inverse B would represent the corresponding vector. In terms of components, eta lowers indices and eta inverse raises indices. Actually, we use the same letter eta to denote eta inverse as well, at least in terms of components. So the equation becomes A upper mu, which is the contravariant version or vector component version of A lower nu, is given by eta upper mu nu A nu. Note that eta inverse happens to be exactly the same matrix as eta, so raising the index works exactly the same way as lowering does. It changes the sign of the spatial components and keeps the temporal component unchanged. it obviously follows that A upper mu, A lower mu, A upper 0, A lower 0 plus A upper 1, A lower 1 plus A upper 2, A lower 2 plus A upper 3, A lower 3, which when written entirely in terms of upper index quantities would be our familiar invariant quantity A0 square minus A1 square minus A2 square minus A3 square. Now, you will often see that textbooks write a 4-vector A mu by breaking it up into two parts, the temporal component A0 and the spatial component, which is also a 3-vector under rotations and is denoted just by A vector. And using this notation, A upper mu B lower mu is simply A naught B naught minus A dot B, where A dot B of course stands for A upper 1 B upper 1 plus A upper 2 B upper 2 plus A upper 3 B upper 3. Now these are results which are pretty straightforward, but they are actually very, very useful in applications. So it is very important that you get used to these results so that you can use them almost without thinking when the need arises. As I have pointed out before, this notation of raising and lowering of indices is really quite consistent. While it was originally meant to basically convert contravariant components or vector components into covariant components or covector components, it turns out that it works in other places as well. For example, it does work in relating the lambda coefficients from where the indices go from top left to bottom right to the case where they go from bottom left to top right. To see this, let's start with the relation L transpose eta L equals eta, which every Lorenz transformation matrix obeys. This obviously can be rewritten in the form L transpose eta L eta inverse equals identity, and that reveals that the matrix eta times L times eta inverse is actually the inverse of L transpose. Remember, the lambda mu nu coefficients with mu indices going from bottom left to top right, or the coefficients of transformation for covectors is exactly this, the elements of L transpose inverse. Now the mu element of L transpose inverse, according to this, is nothing but the sum over rho and sigma going from 0 to 3 of eta's mu rhoth element, L's rho sigmath element, and eta inverses sigma nueth element, and that simply becomes eta mu rho in our conventional way of writing these without the summation sign, lambda rho sigma with the rho sigma indices going from top left to bottom right, times eta sigma nu, where eta sigma nu are of course the sigma nueth element of eta inverse. Now eta upper sigma nu of course raises the sigma index and changes it to nu, whereas the eta mu rho on the left lowers the rho, making it mu, and this changes lambda upper rho lower sigma to lambda lower mu upper nu. The point I am trying to make here is, if you were to take the coefficients lambda rho sigma and raised and lowered the indices as if they were contravariant and covariant indices respectively, you would end up with lambda mu nu, the coefficients of L transpose inverse. So, whereas in general, this just happened to be a convention to write the elements of S transpose inverse, which are the covector transformation elements, it turns out that if you just go by the rules of raising or lowering indices, and if you were to just think of going over from lambda upper rho lower sigma to lambda lower mu upper nu as a process of lowering the index rho and raising the index sigma, it would work just as fine. Now, just in case that this discussion is becoming a bit too abstract for you, let us fall back upon our old friend, the special Lorenz transformation, to make this a bit more concrete. So let us take a look at what happens when you tried raising or lowering the indices of the special Lorenz transformation matrix coefficients so that we can get a better understanding of exactly what this lambda upper mu lower nu to lambda lower mu upper nu transition is all about. Just to remind you, this exactly is the special Lorenz transformation where you are considering two observers. The primed one is moving with a velocity v, which is beta times c, along the x-axis with respect to the unprimed observer. And the transformation, as you all know, is x prime 0 equals gamma times x0 minus beta x1. X prime 1 is gamma times minus beta x0 plus x1. X prime 2 is x2 and x prime 3 is x3. So the matrix L describing this transformation, whose elements are lambda upper mu lower nu, are familiar Lorenz transformation coefficients, is given by gamma minus gamma beta 0, 0 for the 0th row, counting starting from 0. Then you have minus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now this, of course, is the matrix which tells you how coordinates transform, and also, as we have already seen, happens to be the matrix which tells you how vector components would transform. What about covector components? Now, in order to understand how covector components transform, what we need to do is calculate the matrix L transpose inverse. So if you are thinking in terms of the matrix, L is the coordinate transformation matrix or the vector component transformation matrix. The covector component transformation matrix is L transpose inverse. Now for this particular Lorenz transformation, L happens to be a symmetric matrix. Let me warn you that this is a feature of the particular Lorenz transformation chosen. Is not a generic thing for all Lorenz transformations. But this particular one happens to be symmetric, so L transpose is the same as L. So all we need to do to figure out L transpose inverse is invert this matrix. Now inverting a 4x4 matrix may be a not too easy task in general, but this effectively is a 2x2 matrix, so inverting it is really very easy. Also, on purely physical grounds, you should be able to figure out that inverting this particular transformation essentially tells you how to go back from the primed observer to the unprimed observer's measurements. And since all observers are essentially equal, all that changes is that the velocity, which used to be v for the primed observer with respect to the unprimed one, now becomes minus v, which is the velocity of the unprimed observer with respect to the primed one. So all you really need to do to invert this matrix, and actually to calculate L transpose inverse, is change the sign of beta. So we know that L transpose inverse for this particular case must become gamma plus gamma beta 0, 0 plus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now having said that, let us try to now figure out how this is consistent with our notion of lambda lower mu upper nu being something we can obtain by just lowering the mu index and raising the nu index of the L matrices coefficients. Let me remind you once again that because of the particular diagonal form that eta, the lowering matrix, has, the act of lowering a particular index essentially boils down to changing the sign of spatial indices and not changing at all if what you are lowering is a temporal index. Because eta inverse, the matrix which raises indices, happens to be exactly identical to eta, raising of an index also goes the same way. Raising a temporal index does not change anything. Raising a spatial index changes the sign of the quantity on which this index raising is happening. Lowering a So put together, raising or lowering a temporal index does not change the sign of the object. Raising or lowering a spatial index does. So in this case, we can look upon the elements term by term and check which elements are being raised, which are being lowered. For example, here you have lambda 0, 0 with, well, basically you have lambda 0, 0. And here, what you have is lambda 0, 0. So to go from here to here, what you had to do is lower this index 0 and raise this other index. Since both indices that are being raised or lowered are temporal indices, there is no change in sign. 2 plus 1s, of course, make a plus 1. On the other hand, if you look at this element, which is lambda upper 1, lower 1, and try to figure out from there what this element, which is lambda lower 1, upper 1, is going to be, note that you have actually lowered this index 1 and raised this index 1 to get here. However, in this case, lowering and raising are both being done for spatial indices. Each of these is accompanied by a minus sign, and so overall you get a plus sign once again. So the transformed matrix has element of a plus gamma in this position. On the other hand, if you take a look at this, which is lambda 0, 1, and you compare it with this one, which is lambda 0, 1, what you have done is lowered the temporal index 0 and raised the spatial index 1. Lowering the temporal index does not change sign, whereas raising the spatial index does. As a result, what used to be minus gamma beta has become plus gamma beta. To summarize, if you are raising or lowering the indices to go from lambda upper mu lower mu to lambda lower mu upper mu, as long as you are doing it for the 0, 0 element or for any of the ij elements, that is any of the purely spatial elements, you do not get a change in sign. In the first case, because 2 pluses make a plus. In the second case, for purely spatial indices, it's because 2 minuses also make a plus. So where do you expect a change? The change actually will occur in all the elements which have one index which is temporal, the other which is spatial, which of course means the elements 0, 1, 0, 2, 0, 3 or 1, 0, 2, 0, 3, 0. So these are the elements which change sign. Of course, in our example, many of these elements were 0, so their changed sign version was 0 again. But at least we could see that the minus gamma betas in the original Lorentz matrix became plus gamma betas when you were talking about L transpose inverse or the Covector Transformation matrix. So let me just show how this works in action. Because this particular special Lorentz transformation carries out this particular transformation on coordinates, as far as vectors are concerned, the same matrix is used. So as far as vector components are concerned, what you have is A prime upper 0 is gamma times A0 minus beta A1. Remember, all you have to do is replace x's by a's and x primes by a primes. Similarly, A prime upper 1 is gamma times minus beta A0 plus A1. A prime upper 2 is the same as A upper 2. A prime 3 is A3. This is what we have for vector components or raised indices. What about covector components? So if you are talking about covector A prime 0, A prime 1, A prime 2, A prime 3 are the new components in the new frame. And now the transformation is going to occur according to the matrix which is actually L transpose inverse, or essentially the matrix whose components are written from bottom left to top right. That is our second matrix, the matrix in blue here. So now A prime lower 0 will be gamma times A prime A lower 0 plus beta A1. A prime lower 1 will be gamma times beta A0 plus A1. A prime lower 2 will be A2. A prime lower 3 will be A3. Now, the transformation equations I have written down above are equally valid for all 4 vectors and 4 covectors, at least under the special Lorenz transformation. However, the fact that we have used the same letter capital A to indicate both the vector and the covector seems to suggest that we are talking about vector and covector versions of the same entity. In other words, it's possible that we have obtained the components A lower 0, lower 1, lower 2, lower 3, that is A sub mu, the covector components, by lowering the index from A upper mu. Now, if we had done that, then of course the transformation rules for the covector components should automatically follow from those of the vector components. Let me just show you that that is actually what happens. Take for example A0. Under the special Lorenz transformation, A lower 0 prime, the covector component prime, is of course the same as the A upper 0 prime, A prime 0, for the simple reason that if you are lowering the temporal index, the sign does not change. And we already have seen from the vector transformation equation that A prime upper 0 is gamma A upper 0 minus beta A upper 1. But now, let us rewrite these things in terms of the covector components. A upper 0 is exactly the same as A lower 0, whereas A upper 1 and A lower 1 differ by a change of sign. So, A prime 0 works out to be gamma times A 0 plus beta A1 when we are talking of covariant indices or lower indices. And that is exactly the transformation equation that we wrote down a while earlier. Just to check that this also works for spatial components, let's consider A lower 1. A lower 1 prime is of course the same as minus A upper 1 prime, and that according to the vector transformation equation under the special Lorenz transformation becomes minus gamma times minus beta A upper 0 plus A upper 1, and rewriting everything in terms of covector components again, this simply becomes gamma times plus beta A lower 0, the two minuses of course giving a plus, and there is no sign change when you lower the temporal index. The sign change that happens when you lower the spatial index 1 leads to a plus A1 in the formula there, which again replicates exactly the covector transformation rule that we had written down earlier. Now, while there is no mystery here, after all, we have already seen that the covector transformation coefficients can be obtained from the vector transformation coefficients by suitably lowering and raising indices. This is at least a direct demonstration for a particular case that this is exactly what happens. Throughout this lecture, I have been talking about vector and covector versions under Lorenz transformations, what we usually call 4 vectors and 4 covectors, and I have talked about the connection. We have also of course seen that we can lower indices using the metric tensor eta mu nu. We have not actually talked about the metric tensor yet. This would be our first example of a tensor beyond the rank 0 and rank 1 tensors, that is scalars and vectors. And I am in a bit of a dilemma here because we have not started to talk about tensors proper, at least tensors of higher rank, in this series of lectures at this point of time. So talking about the metric tensor as a tensor is a bit premature. However, we will talk about tensors of higher rank soon, and let me just take this opportunity to introduce a very important kind of tensor of higher rank to you. This is in connection with the question that may have arisen in many of your minds. Can we just raise or lower indices only for 4 covectors and 4 vectors? Since we write vector components with an upper index always and covector components as lower indices, can't we get a covector version of a vector under any kind of transformation, or is this just reserved for Lorenz transformations? If you look at the way in which we arrived at the covector version of a given vector for Lorenz transformations, you would realize that the basic theme was that you could use a vector to get numbers linearly from other vectors using the inner product eta mu nu a upper mu b upper nu, and that told us that the components eta mu nu a upper mu essentially behave like components of a covector simply because contracting with b upper mu is giving us a scalar. Now that was a property specifically of Lorenz transformations. So if under other transformations we have similar quantities, things which are bilinear products of the components of 2 vectors, which yields a scalar, this would be the starting point for relating vectors and corresponding covectors. When I say bilinear, I mean if you replace either of the 2 vector components by linear combinations, the result becomes a linear combination. In general, the quantity G11 A1 B1 plus G12 A1 B2 plus all the way up to Gn and An Bn, where all the components of Ai are multiplied by all components of Bj and weighted by some factor Gij and summed over, yielding us the sum Gij Ai Bj. This could be a possible candidate for a scalar, at least for specific kind of components Gij. Now, because we have used matrices quite often to talk about this kind of combination, let us again do that here. If I form a matrix with components G11, G12 up to G1n along the first row and so on, an n by n matrix with elements Gij, then it is easy to check that if you think of the vector components A1, A2, A3, An and B1, B2, B3, Bn written down into column vectors capital A and capital B, then this expression is nothing but A transpose G capital B. One more very important point. We expect this quantity A transpose GB to essentially be the inner product for the kind of vector space that we are talking about. In other words, this should be a bilinear symmetric product of 2 vectors, and one very important property of an inner product is that it has to be symmetric. That is, if you interchanged the 2 vectors, you should get the same result. And this, in terms of our A transpose GB prescription, simply turns out to be A transpose GB, which is A comma B, must be equal to B transpose GA, which is B comma A. Now, note that B transpose GA as well as A transpose GB are actually 1 by 1 matrices, which is why we have not distinguished them from numbers. Now, a 1 by 1 matrix is of course equal to its transpose. What that means is this expression here is exactly the same as B transpose GA's transpose, and using the standard property of transposes, this is A transpose G transpose B. So the demand that this be a symmetric inner product translates to this, that A transpose GB must be the same as A transpose G transpose B for all A and B vectors. This implies that G must be equal to its transpose, or in terms of components, this tells us that Gij must be the same as Gji. This is a very important property of the matrix tensor, and we are going to see that this plays a very important role in the theory as we go along. Now, the reason why we are looking at such a combination is that we want this combination to be a scalar under the coordinate transformation x goes to x prime equals sx, where s is some linear transformation. We will soon see how to generalize this to nonlinear transformations too. Of course, under this, a and b being vectors transform to a goes to a prime equals sa and b goes to b prime equals sb. Same transformation as the coordinates. What we want is under this, the quantity a prime transpose g prime b prime be the same as the quantity a transpose gb. In other words, we want this quantity a transpose gb to be a scalar under this particular transformation. However, what we have to ask ourselves is, when x goes to x prime equals sx, what happens to g? Does g stay the same or does it go over to some other new matrix g prime? Or in terms of components, do the components gij stay the same or do they change to g prime ij? Well, the way to answer that would be to follow up on our demand that a prime transpose g prime b prime has to be the same as a transpose gb, and let us see exactly what this tells us about the way g and g prime are related. Now all you have to do is write a prime transpose as sa transpose and b prime as sb, and you end up with the equation sa transpose g prime sb is a transpose gb, and this has to be true for all n vectors a and b, all column vectors a and b. Now this immediately tells us, using the standard rules of transposition of matrices as always, that A transpose times S transpose G prime S times B is A transpose GB. If we were being mathematically very pedantic, I would have to point out that not only are we using the standard property that under transposition, the order of matrices in a product reverses, we are also using the fact that matrix multiplication is associative so that we can put brackets wherever we want. Now, since this has to be true irrespective of which A and which B you use, and also the fact that both S transpose G prime S and G are symmetric matrices, it immediately gives us the result that S transpose G prime S has to be equal to G, which can be rewritten simply as G prime equals S transpose inverse G S inverse. Now this looks like a pretty ugly kind of transformation equation, definitely different from the kinds of transformation equations that we have seen before. In particular, it has two S's, not one. Both vectors and covectors that we have dealt with so far transform under transformation x prime equals Sx by using one S matrix, either S directly for the case of vectors or S transpose inverse for the case of covectors. Here we are seeing a S transpose inverse definitely, but in addition to that we are actually seeing another S inverse sitting on the right. So two S's. This gives us a hint that this object would ultimately end up being a rank 2 tensor. Actually rank 0, 2 tensor, but that is something we are going to discuss in detail only in the next lecture. For the time being, let us just see what exactly does this matrix equation tell us about the components of G prime. Now, if you just take the ijth element of this matrix, we get G prime ij must be the sum over both K and L of the ikth element of St inverse times the klth element of G times the ljth element of S inverse. This is just standard matrix multiplication. I've done nothing else here. Now, let me point out that at this stage, because we are using the summation symbol, sigma symbol explicitly. We are not using the summation convention at this stage, and we are not bothered about the placement of the indices. We are just writing everything as. Now we can begin identifying the elements that are sitting there in this equation in order that this becomes suitable for use in the summation convention, especially the upstairs downstairs rule. Now we have already met the S transpose inverse matrix before in the Covector transformation, and we have already used the convention, and we have used the convention that the ith element of S transpose inverse will be written S lower I upper k. So that's one of the factors. What about S inverse's Ljth element? For that, you have to realize that S inverse's Ljth element is nothing but the JLth element of S transpose inverse, and that again can be written down as S lower j upper L. So G prime ij using summation convention becomes S lower I upper k times S lower j upper L times GKL, of course summed up over K and L. So this means that G in a way transforms like twice a vector, so to speak. That is, wherever this transformation equation says that somehow G is like twice a vector. This transformation equation indicates that somehow G is like the product of two covectors, each one picking up one factor of S lower I upper k or something similar, and that is why G prime ij has two such factors. Now, we will elaborate on this in detail in the next lecture, but for the time being, let me just say that because of the fact that this has two covector indices, G is called a 0,2 tensor. Why 0,2? Simply because it behaves like it has two covector indices or lower indices. You could have second rank tensors which have two upper indices, where the transformation coefficients would be S upper I lower k and S upper j lower L. You could also have a mixed tensor like a 1,1 tensor with one upper index and another lower index. What is important is not really where you place the index, but exactly how the components transform. Here, the components transform like the components of G transform with two covector transformation coefficients. That is exactly why it's a 0,2 tensor. We will meet tensors of higher rank formally in the next lecture, as I've been promising, and then you will see that all of this comes together rather nicely. What has all this got to do with the lowering of indices? Well, what we have just said is that this particular combination, a bilinear product, A transpose GB, is a scalar. We can of course think of this as A transpose G, the row vector, acting on B gives you a scalar. In other words, A transpose G essentially acts like a covector. And as we have always done before, if we want to write this entity in its corresponding column vector form, that's a transpose of A transpose G, that will give us components of covector written down in a column, and that will of course be the transpose G transpose capital A, but since G is symmetric, it is the same as G times capital A. So if you take a vector and write it as a column matrix with coefficients A upper 1, A upper 2, A upper 3 up to A upper n, and multiply that particular column matrix by the matrix G, you are going to get a new column matrix whose components will be A lower 1, A lower 2 up to A lower n. In terms of components, A lower I will be G, I, J, A upper j, where the sum of course is over j. And this is what tells us that just like eta mu nu lowered an index for a fourth vector, G, I, J lowers indices for any vector under a general linear transformation. How do you get back to upper indices? That's easy. All you have to do is use G inverse. So G inverse acts on covector components to give vector components. So A upper I is G inverse ijth element times Aj summed over J, and again to keep parity with our convention of balancing indices on both sides and summing up over only upstairs downstairs indices, we write G inverse ijth elements as G upper ij. Note that for the Lorentz case, we had eta upper mu nu as the components which were raising indices, and eta lower mu nu was used to lower indices. But they happen to be exactly the same numerically. That was because simply our eta matrix was self-inverse. That would not be the case in general. So G inverse and G would be different matrices, and the placement of the indices would once again tell you exactly which particular matrix you are really talking about. And of course, because G upper ij is the ijth element of G inverse and G lower jk is the jkth element of G, G upper ij, G lower jk contracted, at least summed up over J, would simply give you the ikth element of the identity matrix, the product G inverse, and that is delta ik. This is a formula that we will need several times later on. To sum up, in order to talk about an inner product under a general coordinate transformation, at least under a general linear coordinate transformation that we have discussed so far, what we need is an additional object called the metric. This can be written down in the form of an n by n matrix, as we have seen so far, making the scalar combination of A and B equal to A transpose GB, and then we could use G to lower indices convert vectors to covectors, and G inverse to raise indices convert covectors to vectors. Let us now take a look at a few examples of this. In fact, these examples are ones which we have already seen before, but maybe not seen in this language. We will start with one where we did not even talk about a metric at all. That is the case of rotations in 3D. There, of course, the invariant scalar that was produced by forming the combination A1B1 plus A2B2 plus A3B3. That is, only the I equal to J term survived and had a coefficient of 1. I not equal to J term in AIBJ had 0 coefficient. That means that there also we had a G, but the G was so simple that we omitted to mention it. The G there was nothing but the diagonal matrix with 1, 1 and 1 down the diagonal. That is nothing but the 3 by 3 identity matrix. In other words, Gij was simply equal to delta Ij. Let me remind you once again, for rotations, the concept of raising or lowering of indices doesn't really make much sense, because as we have already seen, there is no distinction between vectors and covectors under rotations, indeed under any orthogonal transformation, which includes rotations and reflections. So, the fact that Gij lowers indices is not really very relevant here, at least not non-trivial here. Obviously, Gij being delta Ij, if you were to consider delta Ij Aj, all you are going to get is Ai, exactly the same as the ith component of the column vector, which means lowering of indices will not change anything. And that is exactly what was expected. What is important, however, is to realize that we have said just a while ago that under a coordinate transformation, the metric can also change. But that is not something we had used earlier. When we talked about rotations, we used A1B1 plus A2B2 plus A3B3 for the inner product in the original frame. In the new frame, we used A'1, B'1 plus A'2, B'2 plus A'3, B'3. Exactly the same coefficients, no change whatsoever. Let us just check whether that is consistent with the transformation equation that we had written down for our metric tensor. Once again, I am trying to say tensor with heavy quotes around it simply because we have not really defined a tensor of higher rank so far, but we already have seen exactly how G is supposed to transform. G prime ij under a coordinate transformation x goes to x prime I equal to rij xj must be rik rjl delta kl. Once again, the upstairs downstairs way of writing the coefficient matrices is not essential here simply because for rotations there is no distinction between such indices. But note that rik rjl delta kl simply becomes, using the standard summation properties of the delta symbol, equal to rik rjk, and that is nothing but the ijth element of the matrix R transpose. And because R is orthogonal, R transpose is identity, so we end up with delta ij. The important thing is this matrix tensor that we had written down, this components delta ij, is a numerically invariant second rank tensor under rotations. What that means is, if you have a rank 2 tensor under rotations with components which are delta ij, that is 1 when I is equal to j and 0 when I is not equal to j, in one frame, and you transform the components of the tensor using the transformation rule that we had written down a while ago, you will find that the components refuse to change. So you will find statements like delta ij is a rank 2 tensor. What it really means is that if you take a rank 2 tensor whose components are delta ij in one frame, the components stay delta ij in any frame. That is exactly why we did not bother to even talk about delta ij earlier, or at least we did not bother to identify it as an object which has its own transformation properties. Once again, although we have not really talked about tensors in general right now, we have seen exactly how G transforms, and that tells us that this particular G will not change under the transformation. Another case where we had an invariant metric is the one case that we have talked about throughout this lecture, which is the case of Lorenz transformations. Under Lorenz transformations, we have seen that the invariant scalar that we can produce out of two vectors can be produced only if you use a0, b0 minus a1, b1 minus a2, b2 minus a3, b3. So here the metric G is actually our matrix eta, and G mu nu is equal to eta mu nu. Needless to say, we have switched to Greek indices simply because our indices now run from 0 to 3. So what is the transformation equation that we have here? According to the transformation rule that we just wrote down, G prime lower mu nu is lambda mu rho with lower mu upper rho, lambda nu sigma with lower nu upper sigma, exactly what we wrote down for S a while ago, times G rho sigma. Of course, when I said times, I mean summed up over all rho sigma as well. Now, specifically what we have is lambda mu rho lambda nu sigma eta rho sigma, because G rho sigma in this example is exactly eta rho sigma. It turns out that this sum is exactly equal to eta mu nu, and this of course means that if you start with a metric whose components are the components of eta mu nu and carry out the standard Lorenz transformation of coordinates, hence getting a new version of this metric, you will see that the components of the new version of the metric for the new coordinates are exactly the same as those of the old version. In other words, eta lower mu nu is also a numerically invariant 0, 2 tensor under Lorenz transformations. If you have been paying attention, you should really be crying foul at this stage. This particular property of the lambda coefficients that we have used to prove that eta mu nu is a numerically invariant 0, 2 tensor under Lorenz transformations look very similar to the property of the lambda coefficients that we have already known before, but this is not exactly the same. That one actually was a property of the transformation coefficients for the vector components, that is lambda upper mu lower rho. So where did this come from? Well, this can easily be derived out of that one. This is the familiar property that we had seen before. Eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma. These coefficients, of course, are the vector transformation coefficients, not the covector transformation coefficients which are sitting here. It's easy to see that you can derive one of these equations from the other. To see this, we are starting with this expression right here. All we have done is we have changed the indices mu and nu to alpha and beta respectively. So if this expression is at all correct, this thing here should come out to be eta alpha beta. To see whether that is correct or not, what I do next is start with our defining property of the lambda coefficients. That is, we replace eta rho sigma by this quantity eta mu nu lambda mu rho lambda nu sigma. Of course, we still have lambda alpha rho lambda beta sigma to bring the end up. Notice that we actually change these two indices from mu and nu to alpha and beta simply because mu and nu are being used as dummy indices in the expression for eta rho sigma here. And you cannot confuse a dummy index with another index which is free. Now, having done that, let us take a look at these two terms. The two orange terms written here, I've deliberately written them in orange. Lambda mu rho, lambda alpha rho, written this way, are actually coefficients of inverse matrices which are being multiplied. And so what you end up with is this thing becomes delta mu alpha. And the things in purple here, lambda nu sigma, lambda beta sigma after the summation of over sigma gives you delta nu beta. Finally, using the properties of the delta symbol, this summation becomes trivial. So sum over mu and nu can be carried out absolutely trivially, with the deltas ensuring that mu gets replaced by alpha and nu gets replaced by beta respectively. And so this expression is actually equal to eta alpha beta as promised. The proof that I have just given is actually equivalent to a proof that can be given using matrices, and perhaps the version using matrices is even easier to follow. So let us just take a look at that quickly. We start from the defining property of the Lorenz transformation matrices, LT eta L equals eta, and just rewrite that so that I can bring the eta in the middle of the left hand side out on its own. We hit the equation with L transpose inverse on the left and L inverse on the right, giving us the result eta equals L transpose inverse eta L inverse. From this point on, you should be able to show very easily that in terms of components, this means eta mu nu equals lambda mu rho, lambda nu sigma, eta rho sigma, where the two lambdas are actually the covector transformation coefficients. You should be able to figure this out pretty easily. So let me just leave that as an exercise at this stage. The logical next step would be to talk about general, possibly nonlinear coordinate transformations and stress on exactly how a metric tensor would transform under such transformations and exactly how the presence of a metric tensor would lead to the concept of lowering or raising of indices for vectors and covectors respectively. However, this particular lecture has already run too long, so I will sort of wrap up here. But I do believe that I have already discussed enough about the properties of general linear transformations and its connections with general coordinate transformations for you to be able to figure this out on your own. In any case, in the next lecture we will start with a discussion on tensors in general and try to take a look at the metric tensor as a specific example of a 0, 2 tensor. So we will discuss all this then anyway. So bye till we meet again.